In this video, we're going to introduce the concept of assembly mates. When creating your parts at the sketch level, you often use sketch relations to locate sketch entities within relation to themselves and the origin. In an assembly, though, you want to use assembly mates. For instance, if we control drag and create another instance of this plate, the second instance is free to float about our modeling environment. If we look in the feature tree, you'll see a dash next to it. The first component has an F next to it, which means it's fixed in relation to our assembly environment. If we want to create a relation between these two, we can create an assembly mate. And there are several types of these, which we'll go over in depth in various videos. We have standard mates, we have advanced mates, and we have mechanical mates. Let's take a look at what happens when we apply mates. If we make a coincident relation between these two edges, we make a coincident relation between these two end faces, our plates are located together, but they're still free to move in a degree of freedom that we've left underdefined. It's important to note when creating assembly mates that you need to understand the design intent and the mechanical capabilities of your assemblies. We're able to create a mate that's coincident with these two edges and allows a motion that is not realistic in reality. So it's very important that you understand the concept of mates and also how to apply each of these mates in relation to your own assemblies. We'll talk about all these mates in depth, and hopefully you'll get a good understanding of how these mates can be applied and understand how they can be used to realistically recreate the motion within your assemblies. In this video, let's take a look at the width mate. The hinge assembly on the screen, you'll notice, has tapered edges on its mounting bracket. I've left a large gap between components so we can easily see that nothing is touching. This assembly is not fully defined yet. You can see that we have everything floating around. So the first step we need to do is make the axis for our floating part, along with the axis of our mounting bracket, coincident. This allows the hinge to rotate around, but you can see we still need to locate it in relation to the tapered edges. If we go to our mates category, down to advanced mates, we have a width mate. Width mate will allow you to make a selection based on the sides of the component inside of our hinge, and then the faces on the outside of our hinge. It doesn't matter that these outside faces are tapered, it's simply going to take the difference between each side and make sure that our component is centered. That concludes using the width mate. In this video, we're going to talk about applying a hinge mate. We've opened the hinge assembly, and I've already gone ahead and added the width mate that we talked about in a previous video. I have not added any concentric relationship that allows this part to rotate, because that's going to be taken care of in our hinge mate. Let's go ahead by selecting mate from our assembly tab, opening up our mechanical mates section, and selecting hinge. If we take a look at this selection process, first thing it wants is concentric selections. In this case, because our plate on the side is angled, I'm going to grab temporary center axis of both pieces. This will give us a concentric relationship to allow this part to rotate. The next thing it needs is a coincident relationship. Now in this case, it's not a full mechanical assembly, so there are no touching parts. So I have a plane that's located in my outside bracket piece that allows me to create this mate. So simply selecting plane 3 and then the side of our face creates all the mates needed to rotate this part. The benefit of using a hinge mate is because you can actually specify the angle limits by selecting this specify angle limits checkbox. When we do that, we simply select two faces that will allow us to measure an angle between. We can select a positioning angle, such as 30 degrees, and then we can set limits. For instance, our minimum could be -30 and the maximum can be 30 degrees. This allows you to rotate the part through a sweep of 30 degrees to this direction and 30 degrees to the other direction. Now, as you can see, there's no physical connection between here, so the part's actually stopping at our angle limit. That concludes applying a hinge mate. In this video, let's take a look at applying some of the advanced distance and angle mates. We're using the same coupler assembly we used in our linear coupler video without a linear coupler mate. We want to take a look at how we can use these advanced distance mates to replicate the same type of motion we used in the linear coupler mate. Let's start by applying some positioning mates. So we want to make sure that the end faces are located the same, so we're going to use positioning only. We can do the same thing with this upper plate, and again for positioning only. So now everything is positioned coincident with all the end faces. Let's take a look at how we can apply our advanced distance mate. Go to your advanced mate section and select distance mate. Now you'll notice a few things happen. This first selection box is a position box, and then we have a maximum and a minimum value. Let's start by making a selection. We're going to select the end faces just as we did in our linear coupler mate. But now we want to select 0 for a minimum distance. We're going to select 2 inches for a maximum distance. Again, this is just for positioning here, so I can set this to 0. We're going to hit OK. Next, we want to apply the same distance mate, but this time we're going to use the middle plate and the bottom plate. Again, we're going to set our positioning value to 0. We're going to set our minimum value to 0 and our maximum value to 2 inches. Let's hit OK. Let's take a look at what we've created. The distance mate allows us to create a range of coincident mates. So if we drag this upper plate, as soon as we get to 2 inches, it's going to start moving the lower plate. And as soon as we get to 2 inches between the middle plate and the bottom plate, the assembly is going to be locked. It's fully defined. Once we drag this back, once the end faces are coincident, our minimum value of 0, it's going to start pushing that middle plate. And again, once we get all the way back to 0, it's going to become locked again. Now we can drag the middle plate, because there's a 0 distance here for our minimum value, it's going to move in relation with the upper plate, but you can see as soon as I drag it back, the upper plate is left in place. So this is a good way, again, to replicate that drawer slider motion or any other mechanical motion that might rely on limits. For instance, if you had a slot and a pin inside that slot, you could dictate the length of that motion without using any mechanical interaction between the components. Let's go ahead and suppress the limit on our upper. And let's also suppress coincident number 4. Let's take a look at this motion. We're going to create a coincident relation between this edge and this edge. This allows us to rotate this component up and down. As you can see, the drawer slides in and out. So now what we want to do is go to our advanced mates section. We want to create an advanced angle mate. Our selection is going to be these 2 faces. And it's important that we want to keep the dimension in the correct orientation. So we have a flip dimension and a mate alignment section. You might have to play with these selections based on how the face selection creates the mate on your assembly. What we want to do here is select a minimum value of 0 degrees. Our positioning value is going to be 0 degrees. And our maximum value is going to be 180 degrees. Let's go ahead and hit OK and take a look at what we've created. So as you can see, this allows us to rotate our top plate between 0 and 180 degrees. And we still have that distance limiting mate that we created to limit the middle plate. So this is a great way to create some very complicated motion with some simple relations. In this video, we're going to take a look at applying a rack and pinion mate. We have the rack and pinion assembly open, and you'll notice if you start to move the components that they're actually restrained in our environment. Now this is achieved by, again, using a layout sketch. If we show our layout sketch, you can see that there's a horizontal line and a circle. That allows us to give some mates to the components on the screen and allow them to get the proper rotation before we ever apply a rack and pinion mate. Let's go ahead and select Mate from our Assembly tab, expand our Mechanical Mates section, and select Rack and Pinion. Rack and Pinion is very similar to applying a gear mate. It's simply going to take a relationship between the rotational motion and the linear motion of each component. So you have a few options here. We can do pinion pitch diameter, or we can do rack travel per revolution. For instance, if we select rack travel per revolution, we select our rack, basically this bottom straight edge, and our pinion. I'm going to select the center edge here. You'll notice that as we rotate them, they're not moving in the proper relationship. So if we rotate this around, we can make this a little bit easier. So you can see that we get 1 inch of travel per rotation of our gear. Now this also isn't right. Say we set it to 20 inches. This is a little bit more realistic. But you'll notice that our components are now out of sync. That's okay. All we're going to do is OK this mate, expand our mates folder, suppress it, and rotate our components into an orientation where they do not intersect. And we can unsuppress our mate. Now as we rotate it around, we have the correct orientation between our components, and we have a rack and pinion motion that's created inside of our assembly. In this video, let's take a look at the advanced mate path mate. Let's start a new assembly and insert a few parts. The first part we want to insert is path. By selecting OK, this will be located at the assembly origin. Next, we want to insert another component called inner roller link. Just place this in the assembly somewhere. The last component we want to insert is outer roller link. Next, select inner roller link on the screen, hold down the control key, and left click and drag it. This will copy this instance and place it in our assembly. This is a good opportunity for us to use some of the mates we've already learned about. We can select one of the holes in our inner roller link and the pin on our outer roller link while holding the control key down, and make those concentric. Next, we can do the same with the next set of links. Now we want to make the inside and the outside of our links coincident. Do the same thing with the last set of links. Now we want to drag these a little bit closer to our path. Now we've created a small assembly of 3 chain links, and we want to mate that with our path, the surface, to simulate the motion of a chain and sprocket assembly. So from our mates menu, go down to advanced mates and take a look at the path mate. Now you'll notice that path mate wants a component. Now right now we don't really have a good center point to select for our chain. So what we need to do is exit out of here, expand both inner roller link parts, expand boss extrude 1, and show sketch 1. Now you notice because it's a copy of the same part, it's turned on the sketch in both instances. This is exactly what we need, this center point vertex, to help locate with our path. So now we can go back into our advanced mates, back to path mate, and we can select the center point of a sketch as our component vertex. For our path, we want to use our selection manager. Make sure you use select close loop and select the front edge of our path and hit OK. We can now apply that mate and create another path mate. We want to select the center point of the next point on our link. Selection manager again, select that front edge and hit OK. We need to do this 2 more times by selecting the next selection of vertex in the same path once again. Now you'll probably notice that if you were doing this on 50 or 100 links, it could take quite a while. So later on, I'll show you a little bit different way for us to create this motion. We still need to create one more mate. We need to make sure that the inside face of our links stays parallel by holding the control key down and selecting the front plane. We're going to apply a parallel mate with that plane. So now let's take a look at this from our front view. If I simply drag one of these links, it's going to follow our path just as if it was a chain and sprocket assembly. This is a good way to replicate the motion of a chain and sprocket without having to use SolidWorks calculating the dynamics between all the links, between the sprockets, and even between gravity. Later on, when we create a motion study, I'll show you a chain and sprocket assembly, the driving force, and the interference between each chain link and the sprocket teeth to create the assembly motion. In this video, we're going to take a look at applying a screw mate. A screw mate is often used for assemblies such as this vise, where you turn a handle and that screw, most likely an Acme thread, is going to be moving another component. Now, there are a few things that you need to note when you're creating a screw mate assembly. There needs to be a common face between the two. For instance, this vise piece has to have a hole through it where the threads will be engaged. This is true when you're creating these assemblies for a realistic purpose. So you just need to be sure that you have the proper interaction between your components. Let's take a look at applying this mate. We're going to select Mate from our Assembly tab, expand our mechanical mates, and take a look at the screw mate. Now you'll notice the screw mate also gives us options similar to rack and pinion. We have revolutions per inch or distance per revolution. I'm going to go ahead and say distance per revolution. I'm going to set this to 2 inches, and let's make our selection. So the first thing we need to select is the cylinder of our screw. The second thing we need to select is the cylinder that goes through our vise. So I'm going to right click, select other, and I want to grab the face that will interact with the screw and simply hit OK. So now, as we turn our handle, you'll notice that our vise is moving, but the vise is moving really slow. So let's go ahead and edit that and change our ratio. So we want a distance per revolution to be much larger. So as we turn this screw, you can see that we're actually getting 4 inches per 1 revolution of our handle. That concludes creating a screw mate. In this video, let's take a look at all the available standard assembly mates. We're going to take a look at all the standard mates in one video because they're a little bit easier to handle than the advanced and mechanical mates. On the screen, we have a base plate, which is fixed in our assembly, and we have a floating plate. Let's take a look at the available standard mates from our Assembly tab and see how we can relate these two to each other. The first standard mate available is coincident. Now, coincident can mean several different things. We can make a single point coincident with another point, or we can make a single point coincident with an edge. We can make that point coincident with a plane, or we can make an edge and an edge coincident, an edge and a face, or a face and a face. Now, all these various options will give you a different result when you're dealing with the motion of your assembly, and it's important to understand how that motion is going to be conveyed. The next available mate is parallel. Now, parallel is going to need a straight edge or a planar face. In this case, we can take this edge, make it parallel with another edge. We can make an edge parallel with a face, or we can make a face parallel with a face. The next available option is perpendicular. Perpendicular, again, needs either a planar face or a straight edge. We can do an edge to an edge, which will give us a certain degree of freedom based on the resulting mate. We can do an edge to a planar face, which gives us one less degree of freedom, or we can do a planar face to a planar face. It gives us even less freedom because the plane is defined more in space than the line is. The next available option is tangent. And tangent wants a planar face or an edge in relation to a curved surface. So we're going to take a look at this face